Welcome. In this video, we'll be covering feedback as it pertains to circuits. And we'll also be looking at the four benefits of using feedback within circuits. Let's get started. So as I mentioned, this video will cover an introduction to feedback. We'll start off by looking at the basic feedback structure. So what we have is we have a basic feedback structure shown here. We see that we have an input X sub S, an output X naught, a feedback signal X sub F, and a error signal X sub I. We also have in this circuit a single summing node where we have a plus sign for the signal and the feedback being a negative sign. And we also have the amplifier A shown here, and that's going in this direction, in the left to right direction. Then we have the feedback circuit beta, which is going in the right to left direction. Now, the first thing you notice is we actually have X sub S, X sub F, and X sub I, as opposed to voltages or currents. And the reason for that is these three signals can either be voltage or current, but they all need to be the same type. So if X sub S is a voltage, then the other two are also voltages. If X sub S is a current, then the other two are also currents. So those three will all have to be the same type. The output X sub naught is also either a voltage or a current. So X sub naught is also either a voltage or a current, but it does not have to be the same type as the input ones. So these three being at the inputs have to be the same. X naught is at the output, and it can be a voltage while the other three are currents, or it could be a current while the other three are voltages, or they could all four be voltages or all four currents. We refer to A here as being the open loop amplifier. So what we have is, from an equation wise then, we say we have that X naught here will be A times X sub I. So we have our first equation shown here, equation 1. Beta, which is our feedback portion of the circuit, so we call that the Greek letter beta, so it's referred to as beta. And that will usually be a passive network. So in most feedback circuits, beta is passive. That's not always the case. In some cases, it will be an active circuit. But for the introductory portion of this, we'll assume it's passive. And since it's a passive circuit, we can assume then that beta will be less than 1. So we'll have no gain in the feedback portion. So we can write a couple more equations now. We have that X sub F will be beta times X naught. And also we have X sub I is equal to X sub S minus X sub F, the feedback factor. So these are our other two equations that we have here then. So we have three equations so far. We can combine all these three equations, 1, 2, and 3, and find X out, X naught over X sub S. If we do that, we solve for this, so we define A sub F to be the closed loop gain. So A was the open loop amplifier gain, A sub F is our closed loop gain. It's defined to be the output divided by the input, X sub naught divided by X sub S, our input signal. If we just combine 1, 2, and 3, we'll find that A sub F is then given by A divided by 1 plus A beta. So this is an important formula for the feedback gain, for the closed loop gain for a feedback amplifier. We have some terminology here. We refer to A beta as the loop gain. The reason for that is it's the gain around the loop. If we start here and we go around this loop and back to here again, we see it's A times beta. So we call A beta our loop gain. And because that's so important, we also give it a new parameter, L. And we'll define that to be A beta. And so L is also will be just A times beta, the loop gain. So we define L as our loop gain. Notice that the units for L will always be dimensionless because we're finding the gain around the loop. So it's going to be in units of volts per volt or amps per amps or just unitless. So it's always just a number for this. Because we're always going from, if X sub I is a voltage, then we're finding the gain around back to a voltage. If X sub I was a current, we'll find the gain back around to the current. So it's always a volts per volt or amps per amp. So it'll be a unitless number. So that's our output. We can also write that the error signal X sub I is shown. You can solve this equation and we'll find that it's equal to 1 over 1 plus A beta times X sub S. So this is an interesting result because we see here from this equation here that if A beta is very large and goes to infinity, then X sub I must go to 0. If A beta goes to infinity, X sub I going to 0 implies that X sub F must equal X sub S. So in other words, as our loop gain becomes very large, we will always have this feedback signal becoming pretty much equal to our input signal. So it's forcing that to be equal, and X sub I here is going to 0 as A beta goes to infinity. So let's look at an example here, a non-inverting op-amp example. So in this case, we have our input V sub S here, which is also applied to the positive terminal of our op-amp. We have our output V out. So in this case, our input is a voltage, our output is a voltage. And we have our beta network down here, which was this network here. So we have that the gain from this node V out to our feedback signal V sub F is beta. So beta just works out then to be R1 divided by R1 plus R2. It's just a resistor divider network. We're assuming in this case that our amplifier here has gain A, but infinite input impedance and 0 output impedance. So we don't have to account in this case for any impedance looking up into our amplifier. If this was a practical amplifier, we'd have to include that effect when we're finding beta. So then we have in this circuit that by our equation that we had, that V out divided by Vs is just A divided by 1 plus A beta, where A is the gain of the amplifier and beta is the transfer function for the resistor divider network, or the gain through that resistor divider network. And then we can see that if A beta is much greater than 1, so if A beta here is much larger than 1 at this point, we can ignore the 1 term. So we would have A divided by A beta, which would result in the closed loop gain just becoming, we can ignore the 1, and then the A's would cancel out. So we just have the closed loop gain is equal to 1 over beta, as A beta becomes very, very large. And in this case then, because of beta given by this equation, 1 over beta is equal to 1 plus R2 divided by R1. So our classical result for a non-inverting op-amp amplifier. Just as an example, then if if R2 was equal to 9 kilo ohms and R1 was equal to 1 kilo ohm, find the closed loop gain if the amplifier A was 10 to the 4th, and secondly, if the amplifier gain was equal to 0.8 times 10 to the 4th. So change it by 20% and see how that changes the closed loop gain. So just putting this into these equations here, first off we note that because these are now given to us, we can solve for beta, which is R1 over R1 plus R2, which is 1k divided by 1k plus 9k, so it turns out to be 1 over 10. So A sub f is given by, in our first case, when A is equal to 10 to the fourth, so we're doing this case here, then the closed loop gain is equal to 10 to the fourth, divided by 1 plus 10 to the fourth times beta, which is 1 over 10, and that all works out to be 9.99 volts per volt. In the second case, when we look at A is equal to 0.4 times 10 to the fourth, so we reduce it by 20%, put it through the same equations here, and we get just change A from 10 to the fourth to 0.8 times 10 to the fourth, we end up with the gain becoming 9.9875 volts per volt. So what we noticed that A changed by 20%. So we went from 10 to the fourth down to 0.8 times 10 to the fourth. So it decreased by 20%, but that only resulted in a 0.025% change in the closed loop gain. So we've desensitized our circuit in terms of the amplifier gain A. It can change quite a bit, and the closed loop gain doesn't change too much. So the next thing I'd like to look at is the useful properties of negative feedback. And there's 4 main properties. There's gain desensitivity, which we just saw an example of. We'll look at that in a little more detail. There's bandwidth extension that we'll see. By using feedback, we'll have our closed loop amplifier bandwidth be extended, both in the high frequency and in the low frequency. There's a reduction in nonlinear distortion by using feedback. So if the amplifier A has some nonlinearities in it, putting it into a feedback loop makes the circuit more linear. And finally, we'll see that there's an input and output impedance enhancement. So if it can reduce our output impedance, and it can also increase the input impedance, depending upon how we're using it. It can actually either increase the input impedance or decrease the input impedance, and it can also increase or decrease the output impedance. But generally, it's in the direction that you'd like it to go. So for a voltage input amplifier, it would increase the input impedance, but for a current input amplifier, it would decrease the input impedance. So it helps you in both cases. So let's start off and look at gain desensitivity. So we have from above that the closed loop gain is equal to A divided by 1 plus A beta. We would like to find the derivative of the closed loop gain as we change the amplifier gain A. So we would like to find the delta closed loop gain given that the amplifier gain changes by delta A. So to do that, we can just take the derivative of this formula. But if you notice, there's an A in the numerator and an A in the denominator. So we'll need the quotient rule in order to do that. So we recall a quotient rule for taking the derivative. And that's given this equation here. So if we have the derivative of fx divided by gx, where both are a function of x, with respect to x, so taking the derivative of that, it's given by f prime of x times gx minus f of x times g prime of x, all divided by g squared of x. So you can look that up in any calculus book. So in this case, we have that f of x in the numerator is equal to a. So the numerator here is equal to f of x. The denominator g of x will be 1 plus a beta because that's the denominator up here. So substituting those values, first actually before we substitute those values, we notice that we're going to need f prime of x, and we're going to need g prime of x. So also writing those out, we have that f prime of x, if f of x is equal to a, is just equal to 1. If g of x is equal to 1 plus a beta, then g prime of x, the derivative of g with respect to x, is just equal to beta. The derivative of g with respect to x in this case is equal to a. And that's in both this case. So the derivative of a with respect to a is just equal to 1, and the derivative of 1 plus a beta with respect to a is equal to beta. So x in this case is equal to a. So then, making use of this quotient rule, we have that fx prime is given by this. So we have this is fx prime. We have g of x is given by this, which becomes 1 plus a beta. We have f of x, which is given by this, which becomes a. We have g prime of x, which is given by this, which becomes beta. And that's all divided by g squared of x, which is g of x, again, is equal to this. So that becomes 1 plus a beta squared. So if we just reduce this a bit, we see that the a betas here cancel out. And we have this is equal to this equation here. So the derivative of the closed loop gain with respect to a is 1 over 1 plus a beta squared. Then we can just move the dA up to the numerator over here. We can write that the derivative of a sub f is dA divided by 1 plus a beta squared. Now, this would be fine if we just left it the way it is, and if we had a delta change in a, we can find the delta change in the feedback, closed loop feedback gain. But often we want to find the percentage change. So we have a percentage change in a, so we might say that a changes by 20%, and we want to know what the percentage change is in the closed loop gain. So we'd like to change this slightly. So we can divide both sides of 5 here by a sub f. So this is just taking this part here, divide both sides by a sub f. But we also have that a sub f is equal to this, equal to a divided by 1 plus a beta. And substitute that in for this side over here. If we do that, we end up that the derivative of a sub f with respect to af, so divided by af. So in other words, delta af divided by af, which is a percentage change, will equal 1 over 1 plus a beta times the delta a divided by a, so the percentage change in a. So, as an example, if we're a can change by, let's say, 10%, what size value of a would be required to keep the closed loop gain change less than 1%? We know it's going to be reduced, assuming that the closed loop gain is equal to 20. Also find the beta and also find the closed loop gain if a went to infinity. So if a changed, instead of by 10%, changed immensely, so went all the way to infinity, how much would that change the closed loop gain? So let's start off with the first part. So we have that a sub f is equal to 20, which is given. And we know that a sub f is a divided by 1 plus a beta, and that's equal to 20, and that's given. We also know that from above, we want this value here to be 1%, and this value here would be 10%. So putting that into our equation here, we have that 1% should equal 1 divided by 1 plus a beta times 10%. That tells us that 1 plus a beta should equal 10, because we're trying to get a factor of 10 improvement in our change in the closed loop gain with respect to the change in the open loop gain. That means that 1 plus a beta is equal to 10. We can substitute this into here. And we have that A should be equal to 20 times 1 plus A beta. So A must be equal to 200 in this case. So we have that A is equal to 200 and 1 plus A beta is equal to 10. And we can put those two together and we have that 1 plus A beta should equal 10. We can solve for beta, and beta must equal 9 divided by 200, or beta is equal to 0.045. So now our last part says if A went to infinity, so if beta stayed the same and A went to infinity, how would that change our closed loop gain? So the closed loop gain right now is given as 20, but let's say A here went to infinity and beta remains the same. So what we have is that if A goes to infinity and beta is equal to 0.045, closed loop gain is A divided by 1 plus A beta. As A goes to infinity, that just becomes 1 over beta, which is 1 over 0.045. So it goes to 22.2 volts per volt. So in other words, we originally designed it to be 20, and we required an A of 200. But if for some reason A became 10,000, it would get higher and higher, but it would never get higher than 22.2. A would have to go to infinity in order to reach finally 22.2. So only a 10% increase in our closed loop gain, even though A could increase a large amount. If A decreases a large amount, that's a different matter, and then it would change more. So the next benefit of feedback that we'd like to look at is bandwidth extension. So we want to take our normal feedback system that we have here. In this case, we'll change A to now be A of S. So make it a function of frequency. So rather than just having A, we change it to be an A of S, which is now a function of frequency. And we're going to leave beta to be a constant. So it will not be a function of frequency. I'd like to see how that affects things. So now if we rewrite our equation, we have our closed loop gain is x naught over xs, which is now A of S times 1 plus A of S times beta. As I mentioned, we're going to leave beta as a constant and not change that as a function of frequency. Now, what are we going to consider for A of S? Well, we've already seen before that an amplifier often has a mid-band region over here. So this might be an amplifier A of S and plotted versus log of frequency. And we would say that the mid-band region would be over this region somewhere, and above omega L or omega H, sorry, above the high frequency cutoff, the output starts to drop at some 20 dB per decade, or perhaps higher if there's higher frequency poles as well. Below omega sub L, the low frequency cutoff, the output starts to drop at minus 20 dB per decade, going to a smaller and smaller frequency. So if we looked at an equation for this, we'd see that the mid-band gain is A sub m, and there'd be two poles, one at omega sub L and one at omega sub H. So a pole due to the low frequency cutoff and a pole due to the high frequency cutoff. But now we've introduced one more term here. That's this term here, S divided by omega L. The reason for that is that as we're in the mid-band region, so when S over omega L is much greater than 1, so we're letting S equal j omega in order to calculate the magnitude of the frequency response. So when j omega over omega L is much greater than 1, then we can ignore this term. And so if we also put this term in here, we'll find that for S, or for j omega much greater than omega L, then this would just have a gain of A sub m divided by 1 plus S over omega H. So that gives us our mid-band region that we'd like to see. So the numerator here is the S, which is due to the low frequency cutoff having a cutoff, or a 0 at DC. Now notice that if omega L went all the way to 0, so in other words, if I started pushing omega L closer and closer to 0, these two here, then this would no longer matter at all. We could just eliminate both those, they divide by each other, and as I mentioned, we would just have the low pass response would be A sub m divided by 1 plus S over omega h. So in other words, as omega L becomes smaller and smaller, we would just have a curve that would look something like this. That would be given by this equation here, as omega L went to 0. And that's shown in this curve right here. Also, if in some case that we omega h went to very large frequencies, so if we could ignore the high frequency component, then A would look like a high pass response rather than a low pass response. It would look like A sub m divided by 1 plus omega L divided by S. So we would have a curve then which would look something like this with omega L. That would be then this curve here, going off like that, assuming omega h here goes higher and higher and goes towards infinity. So those are really the two cases we have. We can treat, and the reason we did this is we can then look at how our feedback is affected by the case where an A is equal to a low pass response, or in other words, one that looks something like this. And then separately, we can look at how the frequency response for a system with feedback looks like when we have a high pass response given by an A that looks something like that. So rather than trying to deal with it as a second order system, we'll deal with it as two first order systems and deal with them just separately to make our calculations a little easier. So, as I mentioned, we could just substitute 2, which is this larger equation, directly into our feedback equation, but it's a second order system and makes things a little more complicated. But we could do that. But in order to make our life a little easier, we'll look at putting in 3 and 4, so this equation and this equation separately, into equation 1, which is our normal feedback equation, so into this equation here. A divided by 1 plus A times beta, where A is now a function of frequency. So let's start off doing the low pass case. So we're going to substitute 3 into 1. So now this becomes the A sub LP. So this is now this equation here that we're substituting in for A of S. So we have A of S divided by 1 plus A of S times beta. If we just do a little bit of manipulations on that, we'll see it's equal to this equation here. Then if we divide the top and the bottom by 1 plus A sub m beta, we end up with this equation now here. Now this looks like a low pass response because we have the 1 term here and S over another value. So we can look at it as a new system, the closed loop gain. But in this case, the midband gain will be A sub m prime and the high frequency cutoff will be omega h prime. And in this case, then A sub m prime will be given by this term here, and omega h prime will be given by this term here. We're just defining, redefining the midband gain and the high frequency cutoff to match this equation that we've just found. Because it's still a first order system with a different midband gain given by the numerator and the 3 dB frequency given by S over that value here. So our new closed loop gain, when we put this in feedback, is equal to the original midband gain of the open loop amplifier, but divided by 1 plus AM times beta. And the 3 dB the closed loop 3 dB frequency. So this was the closed loop midband gain. The closed loop 3 dB frequency is the original open loop or open loop for the amplifier 3 dB frequency, but multiplied by 1 plus A sub m beta. So in other words, if our open loop amplifier looks something like that, then once we put it in feedback, the closed loop one will look something like this, where omega h has been moved to a higher frequency multiplied by 1 plus am times beta, and the DC gain has lowered from a sub m to a sub m prime, which is divided by 1 plus am times beta. So as I mentioned, the gain is dropped by this factor, but the 3 dB frequency has been increased by that same factor. And that's why we consider this to have a bandwidth enhancement. We've improved the high frequency performance by putting this into a feedback loop. Now we want to do the same type of substitution, but in this case now, we'll be substituting in the high pass response. So this will be our A of S. And again, that will get now substituted into this formula here. So we'll deal with now the case where A sub S is a high pass response and see how that affects omega L. So if we go through the math here, and I won't go through all this again, but we're just substituting 4 into 1 now. And all the equations are very similar, but the difference being that when we finally end up with it, that omega sub L prime is now given by this equation, omega L divided by 1 plus am times beta, and A sub m prime is the same as it was before. So our midband gain has changed the same way, but omega L is now divided by 1 plus the loop gain, whereas in the omega h it was multiplied by it. And you can go through the math and see that for yourself. So omega sub L prime is the original omega L divided by 1 plus A beta in this case. So similar to what we saw before, if this was the amplifier gain here, the closed loop gain would become this curve here now. And so it would divide, the midband gain divides by 1 plus AM beta, but omega sub L also divides by 1 plus AM beta. So if you combine 3 and 4, so both the high pass and the low pass together, if we had done equation 2, what we'd see is if the original amplifier looked something like this, when we put it into a feedback system, that the feedback system then would look something like this. So we would see a drop in our midband gain divided by 1 plus AM times beta. But we'd see the 3 dB frequency for the amplifier, which is down in this region, would increase by a factor of 1 plus AM times beta, and the low frequency cutoff of the amplifier would decrease by a factor of 1 plus AM times beta. So we'd get enhancement in the left side, and in the right side here. And so that this just summarizes the 3 results that we have. Omega H gets multiplied, whereas omega L gets divided by 1 plus AM times beta. The next benefit of feedback I want to talk about is distortion reduction. So a linear amplifier would look something like this. So if we plotted, had an amplifier with an input VI and output Vout, and had a gain A, and we'll say that in this case here, Vout over VI was equal to K, so A was equal to K in this case. Then we could plot this. If this is purely linear, it would just be a line going straight through the origin, and it would have a slope of K with respect to 1. So the slope of that would be K, and everything would be perfectly linear. If you put a sine wave in, you get exactly a sinusoidal wave coming out. But now, Consider the case where we used a output buffer. It looks something like this. So these are source followers. So let's say we're driving a fairly small impedance, which means we need a lot of current. So we need a resistance here, which might only be 8 ohms. So it's a loudspeaker, and we need to drive a lot of current into it. So these two transistors would have to be power transistors. So they'd be they could handle a lot of current. So we have these two source followers, but the problem we know is that only when this voltage here gets above a threshold does this transistor even turn on. And then when this voltage here gets also below the threshold for this PMOS transistor, then finally this transistor would turn on. So, but in the middle region here, we would have nothing turning on. So if VI was plotted versus Vout, what we see is that when we're between the threshold of the PMOS and the threshold of the NMOS, the output would just stay at 0. Both transistors, the NMOS and the PMOS, would both be turned off. In this case here, notice this is the NMOS, and this is the PMOS transistor, because these are source followers. And we have a positive power supply up here and a negative power supply at the bottom here. This is not an inverter, it's a source followers. So what we have is we have this deadband region right here, but when the NMOS turns on, then this follows with roughly a gain of 1. When the PMOS one turns on and we go to a very negative voltage, this follows with roughly a gain of 1 as well. So let's take the case where we'll assume that the threshold of the NMOS equals the magnitude of the threshold of the PMOS, and we'll make it equal to 0.5 volts. So in other words, this would be 0.5 volts and this would be negative 0.5 volts. So what we're saying is that in the case where the input voltage here, VI, is between 0.5 and negative 0.5, the output will equal 0. When the input is greater than 0.5, the output will be VI minus 0.5, because we'll just see the voltage across here. Let's say it's equal to the threshold. And let's say we've made our width over length so large that the V overdrive is very, very small. So once it turns on, the V overdrive doesn't change very much. And so we would just have roughly an output which would be V out is equal to VI minus 0.5 volts. And similarly, for the PMOS transistor, when VI is less than negative 0.5 volts, the output voltage will be VI plus 0.5, because we'll always have a 0.5 threshold volt across the source to gate voltage. And as I mentioned then, we're going to have a deadband region right in this region. And the benefit of feedback we'll see is that it reduces this deadband region. So if we have no feedback in this circuit, and we have the case where a positive power supply is 2 volts, negative power supply is minus 2 volts, M1 and M2, and we'll assume, as I mentioned, these are both large power transistors because they need to drive a lot of current. If we applied with no feedback, we just applied the input voltage VI here and looked at the output voltage, then for the input voltage, VI, we would get a voltage which would look something like this. In this case here, we're going up to a value of plus 1 volt and minus 1 volt, and say it's a sinusoidal wave. For the output voltage, we would get a curve that would look something like this. So it would actually be increasing. It would be a dead band, and then it would go up, but it would only reach 0.5 volts because the output is always the input voltage minus 0.5. So if the input goes to 1, it'll only go up to 0.5 and drop down, and then there'll be a dead band region, and then we'll have the same. And so we can see our sine wave is severely distorted in this example. Now what we can do is we can add feedback to improve the situation. So adding feedback, we put an amplifier here, A, and we'll assume that our amplifier in this case, has a gain of 100. Now notice the amplifier does not drive in a large load. The amplifier just has to drive the input of this 2 power transistors. So it doesn't have to drive an 8 ohm load, it's just still driving a high impedances. So it can be regular small signal transistors in here and no power transistors at all in this amplifier. And then we take our output of our circuit. This is where we'd have our 8 ohm resistor, and we connect this back all the way to our feedback circuit over here. So as I mentioned, A is our amplifier, but does not require any large power transistors. Now, again, if we looked at our input is the same as it was before in this case. So this is our input V sub S over here. And our output, we'll see, is actually almost identical to the input. And why is that? That's because if we look at the transfer curve from now from Vs here to Vout, what we'll see is that our deadband gets reduced by a factor of 100 by A. So in other words, rather than this being 0.5 volts on the right, it's now rather than being 0.5 volts on the right, it's now 0.005 volts, and this is negative 0.005 volts. How do we get this reduction in our deadband? Well, if we look at the case, when Vs is equal to 0, Vi will equal 0. So Vs is equal to 0 here. Then this will equal 0. This will be 0, and this will be 0, and it will be in a stable system. So that would be our first case that we have here. But once we make Vs equal to 5 millivolts, the input voltage becomes 5 millivolts. V2 now becomes 0.5 volts. So look at the case now where this is 0.005. This is 0.005, but now this is 0.5. So we're right at the edge of turning on M2. And if Vs goes a little bit higher, M2 will turn on, and Vout will now follow V2 minus 0.5 volts. So that's how our feedback is working. And we see now that, as I mentioned, what Vf will still be 0, but once Vs becomes greater than 5 millivolts, V2 becomes greater than 0.5 volts. So Vout will now start to become V2 minus 0.5 volts. And it will just track that. So in the case where Vs is greater than 5 millivolts, V2 will become greater than 0.5 volts. So we'll have that Vout is equal to, which is equal to Vf because our feedback is directly connected back. And that will now equal V2 minus 0.5 volts. So we can write down some equations. We can say that V1 is Vs minus Vf. V1 being the voltage right at this node. V2 will be 100 times V1. So V2 is 100 times V1. And Vout, we just gave it above, is equal to Vf, which is V2 minus 0.5. So now we have these equations when Vs is greater than 5 millivolts. We can combine those equations. And we can write down then that Vs minus Vout times 100 minus 0.5 has to equal Vout. Solve for Vout with respect to Vs, and we have that Vout is equal to 100 over 101 times Vs minus 0.5 divided by 101. And that becomes the equation when Vs is greater than 5 millivolts, so 0.05. And we can see from this equation that Vout is almost exactly equal to Vs by subtracting a 0.5 divided by 101. So subtract 0.005. So it's very, very close. So when Vs goes to 1, Vout doesn't become 1, but it becomes 1 minus 5 millivolts, which is almost 1. And we get a similar value if you go and you look at the opposite case for Vs becoming less than negative 5 millivolts. So all of this comes about and shows you that we end up with a curve, as I mentioned, which will look something like this. And these are very small now, so our deadband region has been reduced from 0.5 volts to 5 millivolts, plus or minus 5 millivolts. So, going back to distortion reduction, we saw that if we have a linear amp, everything is fine, we have no distortion. But we looked at one case where we had a distortion that looked something like this. And we had a deadband region in this case. But that's not the only type of nonlinearity you might see in an amplifier. In fact, a more common one is shown down here. So we want to look at this type of distortion now of a typical amplifier. A typical amplifier, we see a linear region around the input equal to 0. So again, we have our input and output of an amplifier. But as we go larger, as the output increases, the gain starts to drop off. And eventually, the gain goes to 0 when it becomes horizontal and the output saturates. So this would be a typical amplifier. So it would saturate at some output voltage plus or minus V max. And it would become more and more nonlinear. The gain changes as it approaches V max, and so it has certainly a nonlinear characteristic. The slope of V out versus Vi is the gain of our amplifier. So we can see that the maximum slope is around Vn equal to 0, and the slope decreases as we go to a larger Vn and also a larger Vmax. This variation in gain is really what causes our nonlinear distortion. So we prefer to have a system that might look something like this, that goes straight up and then just comes like that. So it would be it would still saturate at plus minus V max, but it would hopefully be a straight gain the whole time and not be varying. Now, it'd be a little difficult to analyze the system that we have here with this sort of varying gain. We could do it, but we would simulate that probably instead. For analysis purposes, let's look at a similar case. So look at a case here where around Vn we have a gain which is shown here, but once we get the output voltage gets higher than 1 volt, it changes to a different slope here, and once the output is at 2 volts, the slope actually goes to 0. So for this final part, we have the slope, we'll call that gain A3, and we'll say that's equal to 0. But when Vn is very small, so in this region over here, we said we have a gain of 1 divided by 0.01, so we'll have a gain, in this case, the slope is equal to 100. As we get a larger Vn, so as Vn becomes higher than 0.01 and the output is now higher than 1, we have this slope here, and we'll assume that this slope, as this example, we'll say is equal to 25. So say the gain in this region is equal to 25, the gain over here is 0, and the gain over here is 100. So we can see we have varying gains, and we'd like to know what would happen if we took an amplifier that had this type of characteristic for Vn versus Vout, and we put that into a feedback loop and saw what the closed loop feedback gain looked like. So as I mentioned, this is a case where we have a fairly large distortion because our gain is changing from 100 to 25, and then it changes to 0, and finally Vout is greater than 2. So certainly if the output becomes higher than 2, it's going to saturate, and we'll have distortion. So with no feedback, what we see is that the percentage change in our slope is 100 when Vn is very small, to 25 when Vn becomes larger, divided by 100, so we get a minus 75% change in the gain. Well, of course, it goes to minus 100% once we finally reach 0, but let's just worry about the case where it goes from a gain of A1 of 100 to A2 of 25. Now we put this into a feedback loop, as shown here, and we again write our equation for the closed loop gain is equal to A divided by 1 plus A beta. In this case, beta is shown down here, and it's just equal to 1. So beta is equal to 1, so our equation reduces to A divided by 1 plus A. So for when the output is between 0 and 1 volt, we have that A1 is equal to 100. So the closed loop gain is going to be A1 divided by 1 plus A1, where A1 is 100. So it's 100 divided by 101. So the closed loop gain is equal to 0.99 volts per volt. When we go between an output of between 1 volt and 2 volts, so this is the output voltage, the gain now is A2. Put it through the same equations, we see that the closed loop gain during this region is now going to be A2 divided by 1 plus A2, or 25 over 26, and that's 0.962. Finally, when Vout is greater than 2, or trying to be greater than 2, we see that the gain becomes 0, so the gain becomes 0 divided by 1 plus 0, so it's just 0. In fact, we'll see that the output never gets above 2 volts. So what happens if you look now at the input-output relationship from here to here with that amplifier that we just showed, having this transfer curve up here and inserted into this block, and we plot the input-output transfer curve from Vs to Vout, we get a curve that will look something like this, where we now have in this region, between plus and minus 1, the slope is equal to 0.99. Between 1 and 2, the slope is equal to 0.62. And above 2, or at 2, the slope is 0, so it just stays at 2 the entire time, roughly 2. And this change occurs roughly at approximately 1 volt here and approximately 2 volts over here, since we have a gain of around 1. But when it's less than 1, and even 1 when it's between 1 and 2, approximately 1. So our percentage change in slope for this closed loop gain now, so the closed loop slope change, or gain change, is 0.962 minus 0.99 divided by 0.99 times 100. So we only have a minus 3% instead of a minus 75% change in gain. So we get a much smaller percentage change, which results in a much smaller distortion. Of course, this has happened at the expense of lower gain. Our gain now is approximately 1 rather than being a gain of 100. Now the last main benefit for feedback that we're going to look at is the enhancement of the input-output impedance. So they both become enhanced. So in general, what we find is that feedback, it generally improves our input and output impedance. So as an example, we'll just look at 2 examples here, and we'll go into more detail in the next section, next video. In this example here, we'll start off with a non-inverting amplifier. So we have our input Vs applied to the positive terminal, and our output Vout taken over here. We'll assume that the output Vout is equal to A times the positive input here minus the negative input down here. So that's the relationship between the output and the V positive located at this location and V minus located at this location. We also know that from feedback that the output is equal to A divided by 1 plus A beta times Vs. In this case, beta will be given by this circuit that we have here, passive circuit. It's just a resistor divider between this node and Vf. And we see that the beta then is just given by R1 divided by R1 plus R2. Now, we'll also assume that for this amplifier that we have an input differential resistance of R sub D. So, what we want to look at is we want to look at the input resistance, and we want to look at it with and without feedback. So we want to have when there's no feedback involved and when the feedback's attached. So we'll break the feedback and then attach the feedback. So in order to break the feedback, we can let R2 go to infinity. So in other words, let's just open circuit this part here, and we leave R1 as being finite. And then we can see that our feedback is effectively broken, and beta now becomes 0. We can look at that through this equation here. So R2 is open circuited, and we look at the impedance, R in, looking in, we'll just see that the input impedance is going to equal RD plus R1. So we'll just have this relationship here. The input impedance is RD plus R1. Now if both R2 and R1 are both now finite, and we'll let A go to infinity. So we'll look at the case where A becomes very, very large. Then we have that the output is now equal to 1 plus R2 over R1, which we found from before, times Vs. And we also find that V plus becomes equal to V minus. So we have a virtual connection. If you recall, we discussed how as the gain A goes to infinity, that these two voltages will become equal to each other. So in other words, Vs will become equal to Vf, which means that the voltage from here to here must be 0. So if the voltage from there from V plus to V minus is 0, so what we have is that this virtual connection has made V plus equal to V minus. And that's due to feedback in this op-amp circuit as the gain A goes to infinity. Then that means that the current through that resistor here will be 0 because there's no voltage across it as the gain goes to infinity. The gain of the amplifier goes to infinity. That means that if we look at the input impedance, our in must be going to infinity because the input impedance is just the input voltage divided by the current. The current has gone to 0, so the input impedance has gone to infinity. So we see that previously the input impedance was RD plus R1, and now it goes to infinity if we can make the amplifier gain A go to infinity. Notice that does not make the input-output go to infinity. The input-output becomes 1 plus R2 over R1, given by this equation here, even though A goes to infinity. As another example, so that's a case where our input impedance becomes very, very large as A goes to infinity. It becomes infinite as A goes to infinity, and as A becomes large, the input impedance becomes very large. Let's look at another example. In this case, we'll look at a photodiode receiver. So this would be a typical receiver that might be used for TV when you use your remote control, and it uses infrared, and it tries to detect whether infrared light is being shone on it or not, or the same photodiode might be something in a fiber optic cable and looking for light. So a typical infrared receiver is to use an amplifier here in a feedback configuration with a resistor R sub F, and the photodiode is actually shown over here. This photodiode is set up to a voltage down here, which is a negative voltage. The virtual ground will make this voltage equal to the virtual connection between here, which will make the negative terminal also equal to ground, since the positive terminal is equal to ground. So we have that the voltage here is 0 volts, and because this is minus VSS over here, we have a reverse biased across this diode. So when no light shines on this circuit, what we see is that the reverse bias diode on this, the reverse bias voltage on this diode means that no current is flowing. So ID here, so ID here just goes to 0. So we see that the diode's reverse biased. If there's no light, ID goes to 0, and the voltage here just remains at 0. So that's when there's no light. Now it turns out when light shines, so when we have some light shining over here, some infrared light or light that matches the photodiode's wavelengths, then light will shine on the depletion region. They ensure that the depletion region is available to the light. It's visible to the light. The light is shining onto the depletion region. And so this reverse bias diode then ends up creating electron hole pairs because light is now shining into the depletion region, and electron hole pairs get created, and they get created in the depletion region. Because it has a voltage across it, those electrons start to flow to the positive side and the holes flow to the negative side. So we actually get current flow. So ID is no longer 0, but it becomes greater than 0 when light shines. So what we see is that current will actually flow in this direction when light is shining on this photodiode. So let's replace our photodiode with a model. So a typical diode model would be a reverse bias diode model for a photodiode would look something like this on the right. And what we have is we have a current source, which is now dependent upon the light that gets shone on it. So the more the light is, the higher the intensity of the light, the more current will flow. But it also has a small signal resistance across it. So this diode small signal resistance. And this is going down to minus VSS over here. So we put this into our circuit and we get a equivalent circuit that looks something like this. And what we see that if we want to look at their input resistance looking into here. If Rn is much smaller than R sub D, so this current that flows here is going to split and go this direction and possibly back down through RD over here. But if RD becomes a much smaller impedance, if Rn becomes much smaller impedance than R sub D, the small signal resistance of the diode, then we can pretty much ignore the current that's flowing this direction. And all of actually I guess we're flowing the other direction. Sorry, I should have been drawing these the opposite direction here. Should have been drawing them this direction, and this direction, or this direction. Anyway, if Rn is much smaller than R sub D, then we can pretty much ignore this current over here, and this will equal I sub D over here. We still have a virtual connection over here, so V out will just equal I sub D times R sub F. So the output voltage will be just equal to the current through the photodiode times R sub F. So this current here will be I sub RF will equal I sub D in the case where the input impedance is much less than the small signal diode resistance. If that's not the case, you split some of that current and you get a smaller output voltage. So let's look at what that input impedance is. We have from Miller theorem from before that Rn is just equal to Rf divided by 1 minus the gain. In this case, the gain is equal to minus A because we're going into the minus terminal over here. So it becomes divided by 1 plus A. So as A goes to infinity, Rn goes to 0, and we have that the current through that feedback resistor R sub F is equal to the current through the diode, and then V out is equal to ID times RF. So what we see here is that we have a Rn reduction. In this case, the resistance, input resistance is getting smaller, and that's due to feedback. And that ends this introduction into feedback, and we'll go into more detail and some more concrete examples in the next videos.